Good morning, ladies and gentlemen. My name is Kurosh Meshki from Kyoto University. Unfortunately, I cannot be with you today for this presentation. But via this video presentation, I wish to present a discriminative tracker which is empowered by active learning, specifically query by bagging. First, you will see a brief overview on visual tracking, its applications, challenges, and the scope of this work. Then we focus on tracking by detection, review some famous work from its diverse collection of trackers, enumerate some of the major trends and the current trackers, and finally, pinpoint some shortcomings in many of the current tracking by detection methods. Then we have a quick recap on active learning and its well-studied variants, something like query by committee, to promote its benefit to construct a robust ensemble tracker. We also introduced several ideas to enhance different stages of the proposed tracking by detection algorithm. Finally, the results of this algorithm are analyzed, compared with the state of the art, and discussed. Cameras everywhere, from our very rooms with Xbox Kinects to various aspects of our daily lives. When we are driving, when we are using public transportation, when we telecommunicate with friends. In these and many more scenarios, we find objects of interest that we wish to track. This data is useful either in its raw form, like tracking a suspect in the airport for the last 5 minutes, or in the processed form for action recognition, video indexing, and so on. We have come a long way from the dawn of object tracking, yet we are struggling with many fundamental problems in visual tracking, such as illumination variation, scale variations, occlusions and its many forms, complex deformations, motion blurs or fast motions, rotations in many forms such as in-plane rotations or out-of-plane rotations. When the objects are going out of our field of view, or when their background is super cluttered, or even when the target is so small or indistinguishable that we can hardly find a pattern in that to track. And imagine when all of these happen to a poor tracker. When we talk about trackers, we can roughly categorize them as generative ones, where the algorithm tries to reconstruct the model of the target and the target itself, or discriminative ones, when the algorithm tries to separate the target from its background. In each category, there are plenty of iconic studies which keep both schemes attractive. Yet, I feel in the recent years, the discriminative ones are more popular, at least according to several benchmarks like Smulders et al. Or Wu et al. Or VOT Challenge. In this study, we focus on discriminative tracker, especially tracking by detection, in which the tracker employs a classification method to distinguish the target from its background. Recent tracking by detection approaches dive into the depths of the machine learning theories and utilize a variety of methods to do a target-non-target classification. Supervised approaches such as SVMs and boosting have been vastly used in such tasks, whereas semi-supervised and multi-instance learning facilitates this task by relaxing the need to classify each and every sample. A typical tracking by detection algorithm consists of different modules. First, the target object should be presented in a way, usually in the form of a bounding box. Then several samples are selected to serve as candidate for the next target location, considering its motion model, transformation, and this task requires a strategy, for example, Gaussian sampling around the last known position of the target. Every sample is then labeled positive if they can be candidates of being target, or negatives if they represent the local or global neighborhood of the target. This labeling is usually done using heuristic based on distance of the sample to the last known target location or their overlap. In the case of semi-supervised or multi-instance learner, a sample could remain unlabeled. Optionally, some trackers such as TLD by Callor et al. Verifies the labeling of sample by using false positive and false negative sentinels or via co-tracking. The samples with the highest classification score is usually selected as a next target location, and the classifier or classifiers in the case of ensemble tracking are then updated with the labeled sample either for every frame or for every several frames. The latter is called loop strategy anyway. Some fixed trackers decide to rely on the pre-trained classifier or the learning from the first and the only annotated frame and omit this updating stage. So main stages of tracking by detection are representation, sampling, labeling, classification, and updates. There are many tracking by detection studies published every year in major conferences such as ICCV, CBPR, AVSS, and so on. Here we select 5 of them to present a variety of approaches. Online boosting, tracking the invisible or SPT, multi-instance learning tracker, struct or structured output tracking, and LP, label propagation scheme. Arguably, the majority of tracking by detection algorithms, and even some of the latest ones, are suffering from critical shortcomings that degrade their performance in different scenarios. The sampling in search space is sparse, uninformed, and ignores the information contained in each sample about its local neighborhood. In this way, the tracker missed the promising regions of the search space and blindly examined many possible transformations before finding the optimal one. Classifier is trained using all examples with equal weights, meaning that negative examples with overlap very little with the target bounding box are treated equally as those negative examples with significant overlaps. As mentioned, the labeler is typically built upon heuristics and intuitions rather than using the accumulated knowledge about the target, for example. Mistakes in labeling confuses the classifier and is known as label noise problem. Adaptive trackers inherently suffer from the drifting problem. If the update rate is small, the changes of the target are not reflected in the target's template, whereas rapid update of the tracker renders it vulnerable to data noise and a small target localization error. This is an instance of stability plasticity dilemma that is now a hot topic in neural networks like literature. Looking at recent literature on tracking by detection, one can easily distinguish the strong focus on several major problems. 2 of them are the main one: label noise problems and drifting problems. And we have other trends, something like correlation filters, that I'm sure the next talk will elaborate it significantly for you. To address the shortcomings and keep up with the recent trends in the literature, we propose a tracker called QBT that learns from the most informative samples, utilizes an ensemble of trackers to emphasize on various sections of the region space, to construct a robust tracker, rely on samples based on their information content and confidence, shift sampling region of interest to obtain better samples that provides the learners with more information, and embed a hybrid of short-term and long-term memory to address the stability plasticity dilemma. Query by committee is an ensemble-based learner built upon active learning and is supported with a wealth of mathematics and theories. It instantly seems to be the right choice for our goal, as we later figure out that it was. Let me refresh your minds quickly on active learning. In many domains, obtaining data is relatively easy and cheap, but labeling them is rather tedious, complicated, or expensive. Active learning is a discipline of learning that minimizes the number of labels needed to achieve the target error rate. Given a pool of unlabeled data, an active learner selects a subset of samples and asks an expert or oracle about the label. Then it trains itself with the labeled data and chooses the next subset of data in the light of added information to the tracker. By doing so, the learner has been shown to achieve a desired error rate very quickly, sometimes even exponentially faster than random sampling. Let me show you a conceptual demonstration using a linear SVM. In this example, we have several samples indicated by black circles, from which 4 are labeled. Following the maximum margin principle of the SVM, the classification boundary would be like this. The learner then selects which sample to label next. In the case of SVM, this sample is going to be the closest to the boundary line, and among them, the one that is known that could change the boundary more drastically. A new boundary emerged from knowing the label from the sample. And it continues up till we find a desired error rate. Looking at the use of machine learning approaches, we can identify the differences more clearly. First, a sampler extracts several patches from the current frame. These samples are then handed to a labeler and then to the classifier. In the case of supervised classifier, the samples should be labeled either as a positive or negative. Semi-supervised classifiers allow samples to remain unlabeled. Multi-instance learners form bags of samples and determine the label of bag based on the label of majority of samples. Active learners utilize the most informative samples to efficiently and effectively update the learner. And they are going all to the learner. Background, we now can explain the main idea of our proposed tracker. In query by committee, a group of classifiers decide about the label of a sample. If they are unanimous or almost unanimous, then knowing the actual label does not help them to learn a lot. Note that we do not have the actual label and it comes after the sample selection process. On the other hand, when the committee disagrees about the label, the amount of uncertainty of the sample is higher, then it bears greater information about the distribution of the data. So the best candidate for querying next are those with greater uncertainty, the ones over which committee disagrees more. However, using this algorithm is limited to randomized learners to satisfy the Gibbs algorithm, and like all useful problems, it's intractable. Aba and Mamitsuka use the concept of bagging to enable arbitrary-based learners, including deterministic ones, or SVMs, for example, to be combined in a QBC framework, query by committee framework. Bagging is a technique to enhance the performance of the existing learning algorithm by running it many times on a set of resampled data governed by a uniform distribution. The final hypothesis is obtained by taking majority vote over the output of predictions of the output hypothesis. Query by committee and its derivative form a committee from the labeled data from scratch each time they want to decide about unlabeled data, and it's an iterative process. In this study, we propose to keep the committee and teaching it on the go as the new data enters and forms the sample pool. This online version of query by bagging selects a subset of the all arriving data and maximizes the information gain for the learner. This theory to work, we design QBT query by bagging tracker as follows. We employ a size-changing bounding box to represent the target. The first half of the samples are selected around the last known position of the target via a Gaussian sampling. From that point, we employ a gradient descent-like shifting in the sampling center. In the other words, positive samples absorb and negative samples repel the sampling center, proportional to the reverse of their distance to the center. The label of the samples is determined based on the vote of the committee. If they are in agreement about the label, it is assigned to the sample. The most uncertain samples are, however, sent to the oracle for labeling. After being labeled by the committee or the oracle, all positive samples participate in a weighted voting to estimate the target location. The weight of samples is the ratio of committee that voted the sample to be positive. Finally, the committee samples are updated by a random subset of the disputed samples, the uncertain ones. The random subset selection is derived from query by bagging learning. The oracle is updated every 10 frames with all the samples gathered during these frames. This algorithm addresses the shortcoming mentioned earlier in the presentation. The sampling is informed and guided. The committee members are independent and thus could perform classification and updating in parallel. Using oracle to decide about disputed samples reduces the label noise. Weighted voting of the target prevents tracker drift in the event of outlier sample and fortifies the target estimation process. The committee are only updated using disputed samples since they agree for the rest of the samples and adding them to the training sample is redundant. And finally, The loop strategy for Oracle provides a long-term memory that, in cooperation with ever-changing committee members, can balance the stability plasticity equilibrium. Here, the method is illustrated. We have the last known target location. Then we start to sample around it. And after that, we start to shift the sampling center to obtain more positive or more disputed samples. The committee classifies each sample, and we count the votes for each sample for labeling. The most disputed samples are selected by active labeler and sent to Oracle for labeling. Having the label of all samples, we can estimate the next target location. On the other hand, we send all the samples to the sample repository. The sample repository contains two groups: the disputed labels and the undisputed labels. All the labels are sent to the Oracle every several frames to retrain it. The distributed frames for each frame, disputed labels for each frame, are sent to the sampler. A randomized subset of that is used to retrain the committee members, like this, and this, and this. That was all. Marking our proposed method, we use 100 most popular video sequences in the literature gathered in OTB 100 dataset. These videos are attributed with 11 attributes, or as we put them before, visual challenges. And we compared our method with other trackers on all of these videos and each of the categories separately. For comparing our method, we select the state-of-the-art generative and discriminative algorithm as stated in recent benchmarks. To measure the performance of a tracker, the area of the on the curve of the success plot of the trackers is compared. QBT is the red line in this plot, and it is performing better than other trackers overall, and the context tracker in green and struck in blue follows it. As for each category, the results revealed that QBT outperformed other trackers in illumination variation, occlusion, out of view, background clutter, low resolution, in-plane rotation, out-of-plane rotation, subset of the dataset. This can be attributed to the use of active learning for sampling and updating, dual memory scheme that is employed, and having a diverse ensemble of the classifiers that cover various regions of the version space. We also noticed that QBT outperformed others in scale variation, motion blur, and fast motion categories. On top of aforementioned reasons, this good performance can be seen as a result of device-informed sampling and sample averaging. The performance of QBT is comparable to that of the stroke in the deformation case. However, there is room for improvement by allowing QBT to sample from more general forms of transformations, for example, 3D translations or affine transformations. Nevertheless, even in this plot, QBT shows high accuracy tracking more than other trackers. Look at the sharp slope between 0.9 and 1. Here are a few results of the tracker. To conclude this presentation, I want to mention the highlights of this work. We use active learning for tracking by detection that improves sample selection, in which a committee of randomized classifiers chooses the most informative samples. We gave the Oracle a long-term memory to balance the stability plasticity equilibrium. Label noise is reduced by ensemble of classifiers and using query by bagging to update them. Guided sampling promotes the overall performance of the tracker, and finally, the future directions that we are currently working on is mentioned here. In the end, I want to thank you for your attention. Please visit the website. If you have any further questions, there are lots of details about the algorithm. Thank you.